Okay, we should be live now.
Welcome everyone to a new edition of Astronomy on Tap St. Louis. My name is Dr. Andres Plazas Malagon. I'm an astrophysicist at Princeton University and working with the Rubin Observatory. And I'm going to be your host along with my friend, Dr. Alex Haber from the Department of Physics of Washington University in St. Louis. Tonight, we have a special session about the James Webb Space Telescope. But before I continue, I would like to thank our sponsors, the Department of Physics of Washington University in St. Louis, the Academy of Sciences in St. Louis, the Urban Chestnut Brewing Company, the NASA JPL Solar System Ambassadors Program, and the McDonald Center for the Space Sciences. Our first speaker of the night is going to be Dr. Erin May. She's a postdoctoral researcher at Johns Hopkins University Applied Physics Lab, and she's interested in the characterization of exoplanets' atmospheres. Dr. May works with ground and base space telescopes to determine the compositions of their atmospheres and use the 3D climate models to better understand the various physics that affect what we observe. Dr. May did her PhD in astronomy and astrophysics at the University of Michigan. And before she got a degree in astrophysics and mathematics from Michigan State University. Thank you very much, Dr. May, and please go ahead.
Thanks for having me. I'll go ahead and get my screen share started. Yeah, so thanks for that great introduction. I'm an astrophysicist at Johns Hopkins Applied Physics Lab, specifically an observational astrophysicist. So that just means I use the world's most powerful telescopes to study the atmospheres of planets that orbit other stars. And our overall main goal is to answer the question, are we alone? Now, for the most part, we've been stuck observing large planets that are more like the size of Jupiter, but still very unlike anything in our solar system. And the reason I'm here to talk to you today about JWST is because JWST is going to be one of our first steps towards being able to characterize these really small planets so that we can begin to answer this question, are we alone? And are there other habitable planets out in the universe or in galaxy? So I want to start with a brief history of NASA space telescopes. And this is intentionally very brief because I could do a whole talk about a history of space telescopes. So I've limited it to just a few that are relevant to this conversation around JWST, and specifically talking about NASA ones. So the first NASA successful space telescope was launched in 1968, and that was used to study ultraviolet radiation. Ultraviolet radiation is shorter wavelengths than the blue light that we can see with our eyes, or more energetic than what we see with our eyes. So this was the first successful launch. There was obviously attempts before that, but 1968 really started the era of space-based astronomy with NASA. 10 years later, in 1978, was when funding was first approved for the Hubble Space Telescope. And we all are fairly familiar with how amazing Hubble has been, not only in creating all these gorgeous pictures of the universe, but also just helping us learn more about the universe. Hubble was part of a series of 4 observatories called the Great Observatories, which is just named that because it sounds cool, but they also spanned a broad range of light that they looked at, so we could characterize the universe from X-rays out to the infrared heat of the universe. Hubble was originally planned to launch in 1983, and if you're familiar with JWST at all, I'm sure you've heard all of the drama around all of the delays. Well, it's not new. Hubble was also delayed, partially for different reasons. There were some issues with the shuttle at the time that they wanted to make sure was safe before launching both Hubble and more astronauts. So there was in total a 7-year delay from the original launch date to the final launch date in 1990, when Hubble finally made it up into space. Unfortunately for Hubble, when it made it up into space, there were some issues with its mirror, and it ended up needing essentially glasses to repair it. But one of the great things about Hubble is that it orbits Earth, and we were able to successfully repair it, and we've been able to upgrade it over time. Now, in 1996 was when JWST development really began, and the idea came forth, and people began talking about what do we want to do with the next great space telescope, what science do we want to do, and what does that telescope need to look like in order to accomplish that science. So that happened in 1996, 6 years after the launch of Hubble, but funding didn't get distributed for the development and actual building of JWST until 2003. I also want to point out the launch of the Kepler Space Telescope, because this telescope really is the reason that the exoplanet field is where it is. It has discovered about half of the known exoplanets and paved the way for us to begin to think about how we could use JWST for exoplanet science. 2010 was the originally planned launch date for JWST, and I've already hinted at the fact that there's been delays. Well, we're here at the end of 2021, and cross our fingers, it should launch this year. It's been fueled, there's no turning back now. There's been a long road to get here, but we're really excited for where we're going to go with JWST after a successful launch in a little more than a week. So there's a bunch of reasons why JWST is super exciting and going to change the face of astronomy, and I'm going to go through very few of them and also just talk about some fun facts about the instrument and telescope itself. One of the main reasons that JWST is going to be so revolutionary is that it's the largest space telescope ever built. So this is to scale, me standing next to how big the Hubble Space Telescope mirror is compared to how big the JWST mirrors are. JWST is more than 2 times the diameter of HST, which means more than 4 times the collecting area. And that's important because the bigger the mirror, the more light that we can collect from the universe. You can both observe fainter things and you can observe things at higher resolutions. So there's a bunch of reasons why creating a bigger space telescope is useful for helping us understand the universe. Now, although JWST is so much larger in its collecting area than Hubble, it still only weighs about half as much as Hubble does. Still about the size of a school bus, or about the weight of a school bus, but still fairly light compared to HST. And part of that is due to advancements in technology and also the fact that the mirrors were able to be quite a bit thinner than HST's mirrors. Some of the later pictures I'm going to show you also show the sun shield compared to the mirror, and the sun shield itself is about the size of a tennis court. So JWST is absolutely enormous. It's going to collect tons of light from the universe and teach us a whole lot about what's going on. Now, while being so big is awesome for science, it actually leads to some complications with launching. We don't have a launch vehicle for space that can launch a telescope this size without folding it up first. And that is where many of the terrifying things about what's going to happen after JWST launch comes from. So because of its size, it's going to fold up and fit inside an Ariane 5 rocket. Ariane 5 rocket is a European Space Agency rocket, and they are providing the launch free of charge to NASA in exchange for their scientists getting a guaranteed percentage of time on JWST. You can see in these schematics, here is JWST sitting at the top of a rocket, all folded up, very unlike any pictures that you have seen of what JWST is going to look like when it's in space. So because of its size, it's getting folded up, and that means after it launches, it has to unfold. And this is the scary part. There's lots of things that could go wrong, and we're hoping that nothing goes wrong. But part of this includes the fact that the arms that support the sun shield have to unfold. And then the sun shield itself gets tensioned out, which you can see happening right now. And there's several layers to that. And the reason is to help cool the telescope's instruments from the heat of the sun so that we can observe really faint things in the universe. But after the sun shield's tensioned, the secondary mirror is going to unfold and the side mirrors open up as well. And then there's a bunch of other calibration that has to take place to make sure everything is operating properly. All of this happens while it is flying through space on its way to its special orbit at a place called L2. So I mentioned before that Hubble orbits the Earth, and that's great because it means we can service Hubble. When we still had the shuttle, we were able to repair Hubble and we were able to upgrade Hubble. Now, this point called L2 is this gravitationally stable point outside of Earth's orbit. And this GIF is showing JWST flying around, orbiting this point out beyond the Earth-Sun line. The reason that we're putting JWST out there is a few reasons, but some of the benefits include the fact that we can use it 100% of the time. Because Hubble's orbiting the Earth, half of the time it's on the day side of the Earth and we can't use it because the sun is very bright. We can't get rid of the sun, unfortunately. But because JWST is going to be so far away from Earth, we don't have to worry about that, and we can just use it 100% of the time. Also, JWST is going to be looking at some of the faintest objects in the universe, looking for their faint signatures of heat. And the Earth itself is a source of heat, and if we were too close to Earth, JWST would be contaminated by all of the heat coming off of Earth itself. So it's far away, which is great for a few different reasons, but it means we can't service it and we can't ever upgrade it. So JWST has a much more limited lifetime than the Hubble Space Telescope did. Hubble launched in 1990. It's still going strong. Some people might argue it's a little bit less than strong. It's had some struggles in the past year, but there's been great teams keeping it running for us. More than 30 years after launch, it's still doing great science. Unfortunately, JWST only has a prime mission lifetime of 5 years. It has been fueled, I believe, for 11. So we're assuming it's going to last and be collecting science for at least 11 years after launch. Now, L2 is very far away, as you can see, compared to the distance to the moon. It's about 5 times further. And getting there is a very long process. It takes about a month for it to get from Earth to L2. And throughout that process, there's a lot going on. The GIF before that I was showing shows all the unfolding that's happening. That sun shield tensions and gets unfolded within the first 5.5 days after launch. And then by 2 weeks after launch, the mirrors will have all unfolded and be ready to use. After launch, it also takes about a month for the telescope to cool down enough before we can turn on the flight software. And after 2 months, we'll start turning on the guidance sensor, which helps JWST know where it's pointing, and also start turning on some of the first instruments. After 2 months, we'll be able to take the first images, and at this point, the mirrors aren't going to be perfectly aligned yet, so we would expect that these images are going to be blurry. Unlike Hubble, that's okay, because one of the really cool things about JWST is because it's made up of these 18 individual hexagonal mirror segments, each mirror segment can be moved slightly so that they can be aligned absolutely perfectly. So the first image is going to be a little bit blurry because the mirrors might not be perfectly aligned. After 3 months, what's going to happen is each of those mirrors is going to get moved ever so slightly until all of the light lines up perfectly down inside of the instrument bay. It's a cool little GIF from Lego JWST, which is a JWST version of, a Lego version of JWST, which has been fully supported on Lego Ideas. And we're really hoping becomes a real Lego set. So keep an eye out for that. But you can see the little mirror segment wiggling around just like it's going to happen out in space to make the science images perfectly beautiful. So after this happens, we'll get our first science quality images. And assuming there's no further delays with launch and no problems with all of these commissioning, unfolding, alignment processes, our first science quality images are going to come down about 3 months after launch. So that's going to be probably early April or so. You're going to start to see some really beautiful images of space from JWST. But that is not the end of all of the JWST commissioning and getting things ready stage. It's going to take a total of 6 months after launch before we can start using it for science, because there's a lot of tests that need to be done to make sure that the information we're getting back from it about the universe is as accurate as possible. Now that we've talked about a whole process that's going to go on after launch, I want to talk a little bit about the different science themes that JWST is going to be looking at. So it's been designed with 4 major science themes in mind. This doesn't cover all the possible science JWST is going to achieve, but they're the main goals of the mission. The first one is looking at the universe's first light. So immediately after the Big Bang, the universe was really dark, it was opaque, light couldn't travel through the material in the universe very well. And at some point, the universe became transparent, and stars and galaxies began forming, and we began being able to, the universe just lit up at that point. And one of the things JWST is going to do is search for these oldest light sources in the universe to learn more about the formation of the universe. The second major science theme is looking at the evolution of galaxies and how galaxies grow and merge over time. The third one is looking at the formation of stellar systems. Stars are forming from these collapsing nebula of gas in the universe, and the leftover material around them forms a disk that becomes the planets and other things in the stellar system. And JWST is going to be seeking out stars at various stages of formation so that we can study the processes under which stars form and evolve. And the last major science theme is the properties of planetary systems. So this is the one that I'm most excited about because, as I've mentioned, I study exoplanets, which are just planets around other stars. The goal of this science theme is to understand what planets are made of, both the solid part of it and what's in their atmospheres, with the ultimate goal of seeking out the potential for life on other worlds. So looking for these habitable environments in our galaxy. Now, all four of these and all science that JWST is going to do are things that are best studied with infrared light, which is the type of light that JWST is going to be studying. So I mentioned that's why we have to put it so far away from Earth, because infrared light is a type of heat. Now, I've been using the term light, and typically we think of light as what we can see with our eyes. But light actually broadly means anything on the electromagnetic spectrum, which ranges from these high energy gamma rays and X-rays through that visible light that we can see with our eyes and the infrared light that JWST is going to be looking at, all the way out to these microwave and radio waves that are fairly low energy in comparison. Infrared light is special because infrared light is a type of heat, and it lets us see through these really dusty regions in space. Space is fairly dusty, and that means that dust is blocking our ability to see a lot of what's going on out in the universe. This is an example of two images taken with the Hubble Space Telescope with two different instruments. One of them is on the left is taken in visible light. So this is basically what we would see with our eyes if we looked at this nebula in space. And on the right is what that same nebula looks like in the infrared light. So how that nebula and all the stars around it are emitting in heat. You can see so many more stars deep in these dusty regions, deep where stars are beginning to form, that you just can't see in the visible light. So to look at this infrared light, JWST has to have special mirrors. And that is why JWST has these gorgeous gold mirrors. So they're made of beryllium, which is a really strong and heat-resistant metal, and also fairly light. And they're coated in a thin layer of gold, because gold is particularly good at reflecting infrared light. So the reason that JWST looks so pretty is just because of the type of light that we need it to look at. So that's a summary of what's of JWST, what in general is going to look at. And I want to talk very briefly about what it's going to be doing for exoplanets. So since the first exoplanet discovery in 1995, we have detected now over 4,000 planets around other stars. And the rate of discovery is accelerating as new missions come online searching for these planets in our galaxy. We've discovered everything from planets the size of Jupiter orbiting really close to their stars, so they're really hot, and unlike anything that we know, to planets that are about the size of Earth, orbiting the habitable zones of their stars. So environments that might have the potential to host life. And JWST is going to help us study them and understand them and help put our solar system into context so we know how similar or different our solar system is compared to the rest of the planets in our galaxy. So one of the most exciting things that JWST is going to do for exoplanet science is detecting atmospheres on terrestrial exoplanets. To date, we have not yet definitively detected an atmosphere on a terrestrial exoplanet. The best target and the primary target that JWST is going to be using for this is the TRAPPIST-1 system, which is a nearby system of 7 planets, all of them about the size of Earth or a couple times larger, and 2 or 3 of them are in the habitable zone of the star. Now, TRAPPIST-1 is a really cool red star, and it's actually similarly sized to Jupiter. And because of that, these planets have to be much closer to their stars in order to be warm and in the habitable zone. Most of them, I think actually all of them, are going to be observed several times, if not many, many times with JWST. And the goal is to see if any of them have atmospheres. Because having an atmosphere is a necessary thing in order for a planet to be habitable. Now, if we find an atmosphere on these planets, it doesn't necessarily mean that that planet is inhabited, because there's a difference between finding a biosignature or signs that a planet is inhabited, having certain specific gases in its atmosphere, and a difference between that biosignature detection, the habitability or inhabited nature of the planet, versus the planet being habitable and having these habitability indicators like the right temperature for liquid water and having an atmosphere. Unfortunately, JWST is not quite sensitive to these biosignatures, but it's very sensitive to the signs that a planet is habitable and has the potential to host life. And I like to use the analogy that finding a biosignature with JWST is like taking a 5-pound grain of rice, and there's a single one in there that's a different color, and you have to find it with your eyes closed. It's very difficult. It would be a lot easier if we had a magnifying glass, essentially, instead of having our eyes closed, or the grains of rice themselves were bigger. Unfortunately, we don't think JWST is going to be capable of that, but it's really going to pave the way for us to be able to start thinking about what planets are habitable in our galaxy. So with all that said, I'm going to remind you all to mark your calendars. Launch is now set for December 22nd, which is next Wednesday at 7:20 a.m. Eastern. And I know this is the central time zone I'm talking to, so 6:20 a.m. for you. It's very early, but I think it'll be very worth it to get up and watch the launch of this telescope.
Thank you so much for this very fascinating talk. We already have a couple of questions, so I'm going to read the questions to you. So Michi wants to know, how much troubleshooting is possible from so far away?
Yeah, that's a great question to ask. So a lot can be fixed from very far away. So for some examples, the Hubble Space Telescope has had a few problems with its instruments this past year, and the teams on the ground are able to access all of the onboard computers, restart the computers, upload new software to the computers, anything that they need to do to get the instruments back up and running. Now, in the cases of things unfolding and stuff, if something gets stuck in unfolding, I think that's a little bit more difficult because you can't always move things around to unstick something, but I'm sure the teams on the ground are prepared for any scenario that might go wrong during commissioning.
Okay, so there is another question. So this is maybe a 2-part question. I will mix 2 questions. So do we know what the first science target will be? And are all the other science targets already set in stone, or is this going to happen more on the fly? Or how do you get observation time for a telescope like this in the first place?
I do not know what the first science target is for JWST, and maybe someone else here does. Yeah, that's a great question that I'm going to have to look up. As far as getting time on JWST, astronomers apply. Typically, these cycles are every year. The first cycle for JWST, we applied in fall of 2020, so about a year ago. And then panels of astronomers get together and read the proposals and rank them. And that is how we decide what targets JWST is going to look at. Because JWST is a new telescope, there's also early release science that's going to happen fairly quickly after science observations start, which are designed with the goal of getting data into the community's hands as quickly as possible so that we can get all of the code set up to begin to analyze the data as quickly as possible. But At least the first year of observations for JWST has been set. If you go to one of the websites for JWST hosted by Space Telescope Institute, you can look at all of the targets and all of the accepted proposals for the first cycle of observations.
So there's another question in the chat. I think you slightly touched on the planned mission, but there's a question: what is the predicted duration? What's our best case scenario? Is it really to use up all of the fuel, or what will determine how long it will continue to work?
So the prime mission is 5 years. That's how long it is required to last. It has been fueled for 11 years, and that is based on a few assumptions. So the amount of fuel the telescope needs depends on how much it has to spin around between observations. So that fuel is used to change where the telescope is pointing. So the observations are planned in very specific ways to minimize the amount of moving the telescope has to do between observations. So if the observations end up being set up in some perfect way where the telescope barely has to move a lot or anything, it could maybe last a little bit longer than 11 years, but around 11 years is expected to be the maximum lifetime because we have no way to get out there and service it and add more fuel at this point.
So you mentioned the instrument has to be pretty cold. What does cold mean? What temperatures are we talking about? Oh
yeah, gosh, I should know this number off the top of my head. So what the sun shields do is the gold mirror side of JWST is going to be on the side of the sun, not pointing at the sun, so we don't have to worry about how bright the sun is. And then, or sorry, no, the other way, where the basically that sun shield is cooling down the instruments. So there's 5 layers, and each layer gets progressively colder, removing more and more heat from the sun, and it gets down to. So if we're talking in units of Kelvin, 0 degrees Kelvin is absolute zero. That is the coldest anything in the universe can be. And this would be maybe, gosh, does anyone here know a more exact number? I'm gonna estimate around tens of kelvins, very, very cold by comparison. So like minus 250 degrees Celsius or so.
So very, very cold.
Very, very cold. It's basically just, as cold as space. So
Terprai wants to know what measures are in place to protect the telescope from like space debris or from anything that's flying around out there.
Unfortunately, nothing. We don't have little drones that are going to fly around it and intercept any meteorites. But we know from other space telescopes how often it is that they might be impacted by something like that. So the lifetime of JWST is designed so that the mirror shouldn't be significantly damaged in that time frame. Small little nicks from space debris shouldn't be a problem. And for the sun shield as well, there's so many layers that shouldn't be a problem as well.
Okay, I think we have time for one last question. Is there an easy way to change the positioning of the telescope, or can we move it closer or farther away from Earth if we want to?
Unfortunately, no. It's because of that limited amount of fuel. If we wanted to move it any significant amount, we would burn up too much fuel and we wouldn't have enough to do any observations.
Thank you so much. That was really fascinating. I think it's time that I hand back to Andres, that he can introduce our second speaker for the night.
Yes, thank you, Alex, and thank you, Erin. And I just wanted to point out that one of the instruments of JWST, the MIRI, is going to be at 7 Kelvin, which is minus 440 Fahrenheit, which is very, very, very cold. And before that, after that, so I'm going to introduce our second speaker of the night, which is Professor Jeyhan Kartaltepe from the Rochester Institute of Technology, the School of Physics and Astronomy. Dr. Kartaltepe is an expert in the areas of galaxy formation and evolution, galaxy morphologies, galaxy mergers and interactions, and the properties of infrared galaxies. She's a leading member in several large collaborative surveys, such as the Cosmic Evolution Survey, the Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey, and the Cosmic Evolution Early Release Science Survey. She also teaches courses across the undergrad and graduate astrophysics curriculum, and she's also a mentor of undergraduate students, graduate students, and postdocs in a wide range of projects. She's going to talk about exploring the cosmic web with JWST. Thank you, Dr. Kartaltepe, and please go ahead.
All right. Hi, everyone. It is a pleasure to be here today and get to talk to you about our favorite telescope that's going to be launching very soon. So I really want to thank Erin for giving the introduction to JWST previously. She covered a lot of information that now I don't have to. So everyone here already knows a lot about the telescope and what we're expecting. I want to say I'm really excited to be here, and I'm glad that this event is still taking place despite COVID, even in this virtual way. I've always enjoyed Astronomy on Tap events and being to them in person. Maybe someday I'll get to be in person and get to meet some of you. So today I'm going to talk about the two first science themes that Dr. May just told you about, which involve studying galaxies and the very beginnings of our universe. Up here in the upper right, there's a picture of me getting to visit JWST while it was still at NASA Goddard in the clean room there. A lot of astronomers, I think, have selfies of themselves with the telescope because it was a very exciting thing to be able to go visit and see a thing there and think, oh my gosh, someday that is going to be in space. And here's a picture of me with it. So I think it was a very popular thing for astronomers to take selfies with something that, you know, fingers crossed in about 10 days will actually be in space, and we will soon get to use it. All right, so I'm going to jump right in and start talking about galaxies. So before I tell you what JWST is going to do, I want to give a little bit of an introduction to galaxies themselves. So galaxies are systems of tens of millions to hundreds of billions of stars, gas, and dust that are all bound together by gravity. Many of us are familiar with our own galaxy, which is known as the Milky Way. We see that as this picture here on the right. So if you're lucky enough to live in a place that has really dark skies and you can go outside and look up, you might see a beautiful image like this of the Milky Way stretched across the sky. And it looks like this because we're embedded inside it. So we can't really see its structure in a lot of detail the way we can for other galaxies that are external to our own. To our best guesses, our galaxy looks more like this image here on the left, if we were able to go outside of it and actually view it externally. We have a disk structure, we have these beautiful spiral arms, we have a bulge in the center, we have a bar that goes through it, and many other galaxies have structures similar to this. The nearest large galaxy to our own is Andromeda, and someday in our future, Andromeda and our own Milky Way will merge. But that's a whole other story and a whole other talk. When we look out into the nearby universe, we see galaxies that have a wide range of shapes and sizes. Here's a collection of some of this variety. Despite the variety we see, they have a lot in common with each other, and we can classify them into a few broad categories, right? Typically, some galaxies have disks and spiral arms, the way our own Milky Way does. We call these spiral galaxies. Some of those spiral galaxies have really prominent bulges in their center. Others have a very small bulge. There are also galaxies that look more like this one here on the left. This is an elliptical galaxy. It's basically a big ball of stars and doesn't have a disk or any kind of spiral arms. In addition, there are galaxies that are considered irregular. They're undergoing the process of merging with each other and changing their structure. And so we see these types of galaxies nearby us. And so we want to understand, how did these galaxies actually come to be? Where did they come from? How did they get to have these shapes and the properties that we see around us? This video here is a simulation from the Illustris simulation that shows what early structure in the universe is thought to be like. So you see down here in the lower left, there's a counter that says how many billion years since the Big Bang we're seeing this structure. And all of the little specks in this image or in this video correspond to galaxies embedded in what we call the cosmic web. And so the very early universe was overall very dense and very well distributed, very uniform. But over time, gravity pulled that matter to each other, started to form galaxies, and started to collapse into these larger structures. So in addition to galaxies, we have filamentary structures that connect these galaxies. We have galaxy clusters here at the nodes of these filaments, and galaxies evolve throughout the age of the universe in these different environments. So some galaxies are in these really dense regions, which we call clusters. Some are in these very underdense regions. You don't see any here, but there are galaxies in these very empty regions. The color you're seeing in this simulation shows what happens to the density of gas in the universe as the universe evolves, and it shows what the temperature of that gas is. So whether the gas is cold or warm. And all of this, these bubbles and things you see have to do with the process of stars forming in galaxies. So we want to understand that overall process of galaxy evolution and how it relates to the overall cosmic web in the universe. So Dr. May just gave an overview about JWST, so I don't need to say a lot about the telescope in detail, but it will be the largest telescope that's ever launched into space. And that's exciting just because, it's the biggest, it's great, but being larger is really important for us because that means it can collect more light. And so by collecting more light, it's sensitive to really faint things in the universe. And being larger also means it can see things in more detail. And that's going to be very important. And so this telescope is actually so large, the mirror has to be folded up in order to fit into the spacecraft, as you just saw. So this image shows a comparison of the different mirror sizes from Spitzer, which was in the infrared, Hubble in the visible part of the spectrum, and then JWST down here on the bottom in the infrared. So why the infrared? Why is the infrared so important for us? Well, one reason is that when we're looking at things in the infrared, we're sensitive to dust. And this is really important for star and planet formation, as Dr. May mentioned a little bit in the previous talk. But it's also important for another reason, and this has to do with something called cosmological redshifting. So light from very distant galaxies is actually light that's emitted in the visible part of the spectrum that we would in principle be able to see is actually shifted toward a redder part of the spectrum or into the infrared part of the spectrum. And this has to do with the expansion of the universe. So because the universe is expanding, distant galaxies are moving away from us. And that motion creates a Doppler shift in the wavelength of light that we see. So that light all gets shifted toward the infrared. So if we want to study really distant galaxies and we want to compare them to galaxies that are nearby to understand their properties, we really want to be observing them in the infrared because that's where they're going to be very luminous and we'd have a good direct comparison. So what is JWST going to learn? Well, we're going to learn more about the beginnings of our very own universe. And we'll do this by observing light from some of the first stars and galaxies to have ever formed. Now, this sounds kind of crazy, right? How are we observing some of the first things that ever formed? Well, it turns out that light takes time to travel through space. So it takes light 8 minutes to reach us from the sun. So if we go outside and we see the sun, we're actually seeing the sun as it was 8 minutes ago. We're not seeing it at that exact moment. And the more distant something is, the longer it takes light to travel. So light from galaxies can take millions or billions of years to reach us because these galaxies are at such vast distances. And so I like to liken this to saying having a telescope is really like having a time machine. We are literally viewing into the past when we're looking at distant galaxies. We're seeing them as they were millions or billions of years ago and not as they were today. So that means we can actually watch the process of galaxies evolve over time. And we can see some of the most distant stars and galaxies as the earliest stars and galaxies to have formed in the universe, which is very exciting. And so this image kind of illustrates that concept. Here we have the Hubble Space Telescope here on the left, peering into one patch of the sky. These are actually galaxies selected from the Hubble Deep Field, which many of you have probably seen. On the bottom here is the time after the Big Bang that we would be observing those galaxies at. So galaxies today, 13.7 billion years after the Big Bang, all the way here to the right, 200 million years after the Big Bang. And in red, we have something called redshift. And so redshift is how we measure how much that light has shifted into the infrared part of the spectrum. So the larger the redshift, the more distant the galaxy, and therefore the earlier in the universe's history that we're observing those galaxies. And so Hubble has been able to see galaxies that are pretty far away. Some of the, we've seen many galaxies all the way out to here, on the order of 800 million years after the Big Bang. You can compare that with many other surveys. So back in the 1990s, early 90s, before Hubble launched, we were only able to see here to about a redshift of 1 or about 6 billion years after the Big Bang. The Hubble Deep Field was able to see a little bit farther. The Hubble Ultra Deep Field, even farther still. And then with the James Webb Space Telescope, we'll be able to see farther than has ever been possible. Right? So we'll be able to look all the way to about nearly 200 million years after the Big Bang and find the true record holders, right? The very early galaxies in the universe. We're also going to be able to study how galaxies formed and how they evolved over time. So not only are we going to be able to see the most extreme galaxies in the early universe, but when we observe galaxies, we'll see them at all different distances to us. And from that, we'll be able to piece together a timeline of how galaxies changed and grew over the age of the universe. So here is a collection of images from the Hubble Space Telescope, from some previous surveys that show what galaxy structures look like at different distances from us. So these are galaxies in the nearby universe at redshift of 0, so at a time of today, where we have these galaxies that look like spirals and these galaxies here that look like ellipticals. If we look at galaxies that are redshift, say 0.3 to 0.7, so these are about 4 billion years in the past that we're looking, we see galaxies that have a similar structure. We see some spiral structure here. And if we go even further back, so this is about the highest redshift at which Hubble's really able to discern what the shapes of these galaxies are in detail, so around a redshift of 3. So this is 11 billion years ago. We see that galaxies are similar, right? They're kind of disk-like. You have some that are elliptical-like, but overall they're different. They tend to be messier, they tend to be smaller, they tend to be clumpier, because galaxies have changed their properties from this point in the universe's history until today. And so with the James Webb Space Telescope, we're going to be able to push even farther back and see galaxies in much more detail. So this image shows a set of simulations of what JWST images are expected to look like for a set of galaxies at redshift greater than 6. And so with our Hubble images, galaxies at a redshift greater than 6 would look like tiny little smudges, right? We know they're there, but we can't say very much about them. We can't say very much about their structure. But we expect to be able to see a lot more detail with JWST. And if any kind of spiral arms are present, we'd be able to see them. And so by having these really detailed images, we'll be able to say, what were galaxies like at even earlier times? When did some of the structures we see in galaxies form, right? When were spiral arms able to form? When were bulges in galaxies able to first form? How important were mergers between galaxies at these very early times? Right? So there's a lot of different questions that having these detailed images will help us to address. All right. And so in the first year of JWST's observations, it's going to observe a survey called Cosmos Webb. And so Cosmos Webb is the largest program that will actually be conducted during cycle 1, and it's going to take 218 hours of observing time in order to observe this field. So this is a program that's led by myself and my collaborator, Caitlin Casey at UT Austin. And we have a team of about 50 astronomers from all over the world that are contributing to this. So here on the right is an image of what we're going to survey. So this background grayscale image shows a Hubble Space Telescope mosaic. So that means it's a sequence of a lot of images from Hubble that have been stitched together that cover a large area of the sky. And so that's shown in comparison to the full moon. So all of you are probably familiar with what the full moon looks like. So if you imagine the full moon on the sky and you stitch together a bunch of those full moons, you can imagine how big of an area Hubble has actually observed. And so with JWST, we're going to observe the central portion of that. So in blue is the area we're going to observe with NIRCam. So that's the near infrared image, an area of 0.6 square degrees. And in red shows the region we're going to observe with the mid-infrared instrument in the mid-infrared part of the sky. When JWST was first being designed and people were first thinking about what they were going to do with it, I think no one really thought surveys like this were going to be possible, right? I think a lot of people thought, we'll look at pointed things, we'll look in one area here, we'll look at one area here. And so the idea of being able to map out a large area of the sky is very exciting. And so this survey is intended as a community legacy survey. This is something known as a treasury program. So all of the data are going to be public immediately. And our team is committed to releasing data products very quickly. So that means the images that we've calibrated and stitched together will be made available to the public, and any measurements we make from the data will be made available to the public. So in cycle one for this area of research, JWST is actually going to image a lot of different areas of the sky. So for those that study galaxies and galaxy evolution, we refer to this as the extragalactic wedding cake. That means you want some surveys that cover a wide area and are relatively shallow and observed for less time in a given area. And you want some surveys that are much smaller in area but probe deeper, right? So something like the Hubble Ultra Deep Field is the top tier of this wedding cake strategy, where you look in one part of the sky for as long as you can in order to see the faintest things. And something like Cosmos is the bottom tier of this wedding cake, where you want to map out a large area of the sky. Maybe not as deeply, maybe you don't see the faintest things, but you cover many, many more galaxies, and you can see things like galaxy clusters and rare sources that you might miss when you look in one place. Ideally, you want to do all of these. And what's fantastic about the first year of observations that were selected is that JWST will do that. It will cover Cosmos Webb as the bottom tier of this wedding cake. And there are several other survey names, which you may not have heard of, but someday when there's data releases from these surveys and pictures, you'll hear more about them that cover these other tiers. And so this is a truly complementary way of studying galaxies in our universe. So Cosmos Webb has three main science goals that I'm going to talk about very briefly. The first is to identify thousands of galaxies in what we call the epoch of reionization. So we're going to detect thousands of galaxies, map their spatial distribution, and investigate their properties relative to their environment, right? Relative to that cosmic web that I showed before. So to illustrate what I mean by that, if we go back to this picture I showed you before, the epoch of reionization is this fuzzy bit here on the right. And you might ask, why is this fuzzy in this image? And the reason for this is that this is a period of time in the very early universe where it was hard for photons to travel. And so the very early universe would have been neutral overall. That means hydrogen atoms would have been bound. You have an electron and a proton together that readily absorb photons. So a photon can't travel very far before it runs into a hydrogen atom and gets absorbed. So the universe at that time period was opaque. Some people refer to this as the dark ages. So photons couldn't travel very well. As stars started to form, galaxies started to form, and they emitted high energy photons, they were able to go and ionize those atoms and break apart the electrons from the protons and create what we have today, which is an ionized universe, which means photons can travel freely. And we know photons can travel freely because we're able to observe the universe. And so we don't know a lot about this process. We don't know when it started. We don't really know when it ended, how long the whole process took place. We don't know what types of galaxies or what types of stars were responsible for this to happen. And so by detecting thousands of galaxies during this time period, we'll be able to study those questions, right? What types of galaxies actually ionize the universe? Did they happen in galaxies that were in clusters or galaxies that were more isolated? And it really requires mapping out a large area like Cosmos Web in order to be able to answer that question, because we need to know information about the local environment. Another science goal is to identify and characterize rare quiescent galaxies in the first 2 billion years of the universe's history. And what I mean by a quiescent galaxy, these are galaxies that have already evolved. So they have stars and stellar populations that are older than we might expect. They've already stopped forming stars, and we don't really understand why, right? This is something that really confronts our theoretical expectations. So somehow in these galaxies, they had to have formed a lot of stars very early on in the history of the universe and then stop. And then they've evolved ever since then. And so we're going to see how many of these are there. How rare are they? Are they oddballs that we just find every once in a while? Are they more common? And when could they have formed? And that will help us place some constraints on mechanisms to have caused these galaxies to form so quickly in the early stages of the universe. And then our third science goal is to study the relationship between dark matter in our universe and the stellar mass in galaxies and how that's evolved over time. And we're going to do this through something called weak gravitational lensing, which will allow us to create dark matter maps of the universe out to higher redshifts than we've been able to do before. And so we'll be able to study how dark matter in galaxies has evolved over the age of the universe. So this is just 3 things. These 3 probably seem like a lot already. But on top of this, there are an infinite number of science projects that our team wants to do, that the broader community will do. And so by having a data set like this that becomes public immediately, it really enables a huge range of science projects for hundreds of thousands of galaxies that we expect to detect. And that means that astronomers will then be well equipped for cycle 2, for the second year of observations and asking new questions. And we're always expecting the unexpected. I think if you asked people right before Hubble launched what they wanted to do with Hubble, what they thought Hubble's greatest discoveries would be, the things they wrote down would be a very small fraction of what Hubble has actually accomplished, because we've learned so much in that time that we didn't even know to ask back then. And I think the same thing will be true with James Webb. We're going to discover things we never even knew to ask about. And to me, that's one of the most exciting things about such a new groundbreaking telescope like JWST. All right, I'll end there, and I'm happy to answer any questions. Thank you.
Thank you so much. That was really fascinating. And these 2 talks together, I think, give us a really great idea what the James Webb Space Telescope will be able to do. So there are already a couple of questions. The first question is, one wants to know, will JWST be used to do any observations or signs of solar system targets, or will it only be used to look at extra solar system targets?
I think there are programs that look at solar system targets and things like asteroids. I'm not as familiar with that area, but I know there was the whole review panel dedicated to just solar system science. So there are definitely programs to do that.
Another question is, you showed us that you will study the shape of galaxies and so on. So will this maybe in an indirect or in a direct way also help us to learn something about the shape of our galaxy?
Oh, that's a good question. Are we going to learn more about the shape of our galaxy by studying the shapes of other galaxies? I would say yes, in a couple of different ways. I mean, we've learned a lot about the shape of our own galaxy by looking at galaxies nearby us to see what structures are typically like. I think the more important thing is it'll help us learn how the shape of our galaxy came to be. So not just what is that shape, but why is that shape the way it is, right? Why do we have a bulge the way we do? Why do we have a bar? Why do we have spiral arms? I think those are really the questions that JWST will help us with.
One question is, what is the one biggest thing that you are personally excited about the research of JWST for your personal research?
So one Of course, I'm really excited about reionization and these really high redshift galaxies. But the thing that's mostly directly related to my own research are galaxy mergers. So I'm very excited to be able to see galaxies in so much more detail, to be able to study the process of galaxy mergers and what redshift we're able to see them at and how they impact galaxies. So that's the most exciting thing for me.
So I have a question about this very interesting video you showed us a little bit more at the beginning of your talk. So this simulation of the galaxies of our universe in the early beginning. So what kind of models are going into these simulations, and how expensive are they computationally? Is this something I can do on my laptop, or what is the effort that goes into a video like this?
Yes, so that video came from something called the Illustris simulation. And the Illustris simulation required many thousands of hours of CPU time. I don't actually know what the amount of time is, but a really long time. So it's not something that you can do on an individual computer. So a simulation like this involves taking what we know about physics, so things like the laws of motion and how gas particles interact, and what we know about the laws of physics in the very early universe, and then running time forward to see what happens as particles interact with each other, as gravity brings material together, etc. And one of the things that's really nice about a simulation like Illustris is that it encompasses a large volume of space. So on a smaller computer, you could probably do a small volume where you just get one galaxy or a couple of galaxies, but Illustris is able to cover a huge volume and therefore really map out that large cosmic web. And that really requires supercomputers to do well. So it's quite computationally expensive. And
how is gravity modeled in these simulations? Is this a full general relativity simulation, or is post-Newtonian enough, or just Newtonian maybe?
I don't know the details enough. I want to say that it's just Newtonian at this level, because we're not dealing with the very extreme gravity that you would get around, say, binary supermassive black holes or something like that.
Thanks. So we have a little bit a more hypothetical question maybe, but maybe it's still interesting in the chat. So what would happen if we were to point the telescope at a star or an object that it's made out of glass or transparent to light?
Something that was transparent. So it would depend on the properties of that material, right? Because that material might be transparent to visible light, but might not be transparent to other wavelengths. For example, so Dr. May in her talk, she showed an image of what happens when you have dust in the way. And so dust is transparent to infrared light, but not to optical light. I don't know if we know of any material aside from something like dark matter that's transparent to all wavelengths. So that would be interesting.
I think there are no more questions currently in the chat. So I want to thank both our speakers again for this very interesting talk and their presentations. Andres, do you have a couple of words to say at the end?
I just wanted to thank again Professor Kartaltepe and Dr. May for their talks, and I want to encourage our audience to join all of the astronomers in the world, or most of us, on the 22nd, and cross your fingers for a successful launch. And the story won't be over there. You need to still pay attention that it will make it to L2, 1,500,000 kilometers away from the Earth. So this will keep us on edge, but for sure, this is going to be the largest telescope, space telescope ever built. And we are all very excited in the astronomical community for this. So thank you very much for being with us for another edition of Astronomy on Tap. And I hope that everybody has a good evening. See you next time.